today Professor Damir Cavar, who is an associate professor in the Department of Linguistics here at IU. He did his PhD work at University of Potsdam, and he's been here on and off for many years, most recently as associate professor for the last year, I guess.
Yeah.
So thanks so much for agreeing to give a talk. Really looking forward to hearing about your work.
Yeah, so some of you know that stuff. Some people here are involved in the project. I'm talking about the free linguistic environment and what we're doing with that and where we are going with that and why. Let's skip that. The team here, people who are involved or were involved at certain phases. Hai, for example, worked on the project to help us develop a Chinese tokenizer using conditional random field models. Luin is working on Burmese morphology, morphological analyzer, and tokenizer. Ken was involved and might continue to work on Swahili morphologies and grammars to parse Swahili. Tim was partially involved, promised us always that he would help us parallelizing that and making it high-performance computing, working on high-performance computers. Tony is working on morphologies. Daval helped us develop certain parsers for formalisms. Pratik is implementing a machine learning algorithm to guess unknown features of lexical items and so on. I'll say a little bit about that in a second. And we have a lot of people who are advising us, helping us with the development of this project. And some of them were actually in the initial phase involved in developing first versions of the system, like Ken Beasley. Ron Kaplan, who is the vice president of Amazon now, used to work for Xerox in Park, developed the first version of the system that we are reverse engineering here. And Richard Sproat was working on various machine learning, computational morphological systems and algorithms. Ani Zanen, also at Xerox Park with Ron Kaplan, significantly involved in the development of the core algorithms and tools that we are using here. And we got some help from people like Mari Dalrymple, who gave us a complete grammar and morphology for Malagasy that is freely available, actually. We have a complete system for Norwegian. I'm saying complete here because we are talking about broad coverage grammars of a very large scale. So these are grammars. If you run a sentence through the parser, they would most likely 99.9% give you a good parse for the sentence. The Polish system is one of the best grammars or systems around, also freely accessible and available. In addition to that, we have functioning German and English grammars and systems for that parsing technology that I will introduce. We had some help from the BNFC team, BNFC is the compiler that compiles from Bacchus Now form or a specific version of that code that you can then use as parsers using Bison and Flex in the end, actually, for certain formalisms. Seems like I still have to stand here because somehow it does not scroll the way I want that. So what I'm talking about is a formalism that we use in this parser. It's one of the possible formalisms. We'll use various. This one, lexical functional grammar, was developed by Ron Kaplan and a colleague at Stanford a couple of decades ago, actually, as a theoretical framework. And we take it to be an attractive language documentation formalism accessible to general linguists as well as NLP and CL experts, and used in industry, actually. So the current collection of grammars and the parser itself that was developed by Xerox is owned by Microsoft Research, and they had an intention to use it for Bing for deep parsing. It appears to be suitable for computational applications. There are existing grammar engineering platforms, real-world applications for syntactic and semantic parsing, and we consider that technology industry level as opposed to technologies like SPACY or NLTK and so on, which we would not consider industry level. They are toy or educational systems. So the perspective here that I want to sell you is LFG is a very good framework that is extremely powerful for syntactic and semantic processing of natural language cross-linguistically, and it's an ideal platform for what I would call white box NLP modeling and engineering. And the research that we focus on is we want to use LFG-based grammar development for parsing and corpus annotation. We want to generate a system that allows us to quantify over syntactic structures and semantic properties, as well as feature structures and various correlations. You will see a picture of what I mean. I will explain it just in the detail. There's a depth in language that has not been quantified so far at all. And this is what we are trying to reach. We want to build probabilistic models over very deep properties of linguistic units. And it's this environment here, the LFG-based grammar development system and the parsers allow us also to bootstrap resources for low resource languages very quickly. So within a month or two, usually over the summer, for example, if you are interested in working with us on your particular language, we can really bootstrap a functioning system that has real depth to it. For once we would have such a system running over multiple languages, for example, what we can do is extend potential typological studies over the different languages with qualitative and quantitative models for cross-linguistic and intra-linguistic cross-level studies. What that means you will see in a second. Here's the LFG formalism that we might see in the textbooks. What you see here is a set of rules that is basically a context-free backbone. That's a context-free rule that has a left-hand side symbol and a set of right-hand side symbols, and it's augmented with additional functional feature descriptions, where this feature description here, for example, says that if this MP is in this position, I want certain constraints to apply to it. One is that whatever features it has, those have to be integrated into the subject attribute of the dominating mother node. So the left-hand side symbol is the dominating node of all nodes in the right-hand side, given a context-free tree, for example. We assume that there is an attribute value matrix connected with every symbol here, and the symbol S here has an attribute value matrix that has to have a value attribute called subject, and whatever feature is in this MP, it has to be part of that subject. That's what this notation says. Upwards to the dominating node, put my features into this attribute. Whatever else comes from the dominating node, send it downwards to the head of this construction. In addition to that, what we want to ensure is that this noun phrase has to have a case feature, and this case feature has to be set to nominative. This guarantees us that this noun phrase here, say this is in English SOV grammar rule that guarantees subject, verb, object, word order, for example. It guarantees us that this noun phrase is indeed the subject of the clause, if we want to assume it or parse it there. So these are feature and functional constraints that we attach to the context-free grammar backbone, for example. The backbone can be, of course, extended with other formalisms. This is just an example here where we use a context-free backbone. This here just says all my features that I have here in the VP node should be sent up to this dominating node sentence, so the sentence inherits all features from the verb phrase. The verb phrase gets all features from the sentence downwards, right, towards the head. And this we see here, so now the verb phrase basically sends all its features to the verbal head of the verb phrase, and we have an optional noun phrase here. This optional noun phrase requires its features to be attached to the attribute value, to the attribute object in the dominating node, which is the verb phrase. Well, the verb phrase sends all its properties upwards. We have seen that here. So this object attribute actually is the object attribute of the root. Okay, and this is how we explain functional relations in the sentence. We have subjects and objects, for example. And we have features that are inherited through the tree. When we deal with lexical items in this formalism, we assume, for example, feature structure annotation in a very similar way using the same formalism. So we have John, which we label as a category to be of type N for noun, and we assume that these are the feature descriptions for John that we want to send upwards to the head projection. This is a lexical definition, and we have a predicate for John that just says John, so this is sort of this reduced semantics, descriptive semantics that we want to use here. We have number and person features that we need to process upwards. For example, for verbal agreement with a noun and so on, if we are agreeing with the subject. The verb loves here has a similar description. In addition to the morphosyntactic features, we also specify the semantics, or actually the predicate argument structure. So the verb love, the lemma is love, and it requires two arguments, a subject and an object. These slots have to be filled to have a lexical semantics level fulfilled or satisfied in the parse. Okay, so these are very simple descriptive feature structures that we use in these formalisms, and when we parse a sentence like John loves Mary, what we get is a C structure that is basically generated by the context-free backbone, and we get an F structure that is generated by the feature description. If you would have, in principle, every node here in the C structure, in the tree structure, is correlated with or linked to a feature description in the attribute value matrix as well. So the subject here, or the argument of the verb volley, loves, that's just an example to show you another feature or property of this formalism, is the noun phrase John. Its predicate is Ivan in this case, and it's singular. And we have the description of the properties of the verb, present tense, singular, third person. What I just did here is I generated a sentence structure for John loves Mary, and I generated actually a feature structure for John loves Mary as well that will look like that. What we know is that over languages, different languages will have different structural properties at the syntactic level. So Ivan voli Mariu in some Slavic language correlates with John loves Mary nicely. The tree would be the same. Actually, the word order would be the same. But if we take German, for example, Japanese, it would look a little bit different. For those of you who know Japanese, we know that Japanese actually is a verb final language. So it would be John Mary loves in Japanese, right? That different structure would be specific for every language, and we would have a specific context-free backbone for every language, right? But this here would be always the same. We would have some features missing, but the semantic relations and the functions should not vary. The assumption in LFG is that the functional relations in the clause and the core semantics do not vary across languages. So what that means is that we can take this actually to be a bidirectional system. If we have a grammar for English and we have a grammar for Croatian in this example, what we can do is we can parse a sentence, generate an F structure representation for English, translate the predicates and the main predicates in the functional description to the target language, send it back reverse through the grammar of Croatian to generate an output sentence of Croatian. And that's what is going on. That's a big project called Pargram that is in cooperation with Xerox and Microsoft and other big partners that is using this feature structure representation here as some sort of interlingua that matches if your grammars are compatible, if you write them in a similar way using the same attribute notation, the same type of attribute values, you can translate back and forth by just reverting the grammars. Okay? In the next step, I want to show you that using this kind of feature description, we can read out notations that we use, for example, in dependency parse trees, right? So you can map this description here as that's the root predicate, and it has two arguments that are connected to it via subject and object functions, and we can map this to a dependency tree of that type. getting even into more complicated structures if the sentence would be more complicated with modifiers and so on. Okay? So dependency trees or dependency grammar is sort of a subset of LFG that lacks structure, that lacks scope relations that the context-free backbone can give us, that lacks the depth of the feature descriptions and so on that the LFG functional description gives us. Okay? Now, the theory comes with all kinds of constraints that one has to take care of and implement. These are sometimes theoretical constraints that might be less relevant for an implementation of a functioning parser. Lexical integrity means basically the terminal nodes of C structures are morphologically complete words. That means that if you're looking at Chomsky theories, for example, where verbs end up somewhere in the clause, they end up there to collect a suffix, for example, so the word love, the verb love combines with the suffix s by moving to the suffix s and attaching to it and stuff like that. That does not work like that in LFG. We do not assume anything below the word level. There is no structure there. This does not prevent you from doing actually morphological analyses and parsing substructures of lexical items still, right? So that's an independent process. Uniqueness and consistency condition, every F structure is such that every attribute has exactly one value. You can't be plural and singular at the same time and so on. So these are very simple constraints. I will not go through the details. They are very common. And then we have all kinds of constraining equations that we can use that are basically based on the feature structure descriptions in the formalism. So we can have a constraint that says the participle has to have this feature. We can have a negative equation saying that case cannot be nominative on this noun phrase or whatever, or we can write it with a negation operator in front. We can also say that something has to exist. The case feature has to be specified on this word or phrase, but we don't care what case it has. And it cannot be specified and so on. So these are all operations that the grammar allows us. In the rules, we can of course use conjunction operations for the feature structures as well as actually for the symbols and so on for the rules themselves. We can have disjunctions, grouping and optionality and regular expression operators on every symbol and on every feature or feature structure itself. So this is pretty powerful as a mechanism. We can have things, usually LFG does not allow you to assume things that Chomsky type grammars allow you to assume, which is empty projections, empty traces, for example, that are a result of Chomsky transformations or movement operations in syntax. There is one exception, and this is the small pro. The small pro is something that is of equivalent to an invisible subject that is implicitly present. For those of you who know Spanish, for example, hablo español means I speak Spanish, just that I didn't mention that I, so it's an invisible empty pro subject, for example. That is possible in the formalism. And there are certain things that are sort of crucial, and this is basically if you want to deal with one property in language, which is called dislocation or discontinuity. So you can take the object of a sentence like John bought a new car, and you can ask for it. When you ask for it, convert it into an interrogative pronoun, you front it to the sentence initial position, what did John buy, and what you create is basically a long distance dependency between the core underlying position of where this car is, with the verb with which it's connected as an object in its function, right? And it's surfacing somewhere in sentence initial position. This is what we call long distance dependencies, and this is what we call functional uncertainty. In LFG, we have certain regular expressions like this one, for example, which says that we can have something in these positions in a sentence structure. These are place positions or symbols that are placeholders for something like, in this case, subjects or objects, right? So this just says that there could be any long distance path between this and that, and this whatever is in this position should have then a focus feature. Focus features would be things like, imagine in English, I can say, a car John bought, right? So I can front the object and emphasize it and put it into focus to change a little bit the interpretation, say, for example, in a contrastive construction. You can say, John bought a motorcycle, and I could say, no, a car John bought, right? And this is what this rule here expresses, basically. If you do this, if you take the object, subject, or the object, put it into one of these front positions of any clause, wherever they come from any embedded clause deep down in a large sentence, they have to have this feature. That's one of these rules, okay? So this is possible in LFG, but traces are not there. Good. Current situation in NLP, I don't have to explain this to anybody here. Computational linguistics, NLP, is dominated by statistical approaches, machine learning, AI, deep learning, and so on. Let's call this stat NLP. And this started sort of in the 90s and exploded in the second half of the 90s and didn't stop so far. And a lot of problems in NLP basically are considered by all my colleagues. Everybody, whatever I'm asking, you know, this translation problem, this parsing problem, that's all solved. We know all that, right? We have all these evaluation standards by NIST, for example, Parseval, Bleu, Semeval, and so on, and everybody tried their algorithms and approaches, and they are all somewhere 90-something% accurate. We consider this solved. The claims have always been why we need these approaches, why we don't want to have grammar engineering, rule-based models and so on, is they are not robust. These approaches are robust. They are highly accurate. They are more accurate than the old rule-based systems that we used. And you know, there was this famous quote by a famous colleague of ours who said, whenever I fire a linguist, my systems run better. And so the idea was basically over the last 2 decades, linguists and linguistics, these are irrelevant concepts. We don't need that. Machine learning is enough. Well, let me tell you one thing. I'm deeply convinced that this is a fact, that things are changing, and that people start appreciating actually linguistics more in NLP nowadays. There was a false impression that is based on ideas like evaluations and results. Well, evaluations and results of NLP systems, statistical NLP systems, are focused on concrete evaluation data sets, tasks, and methods. We have just a limited set of corpora that are annotated in a very limited way, and this is how we evaluate our algorithms. The data sets are limited to a few languages only. Our resources exist for 1% of the languages, of human languages. We have more than 7,000 languages on this planet. Half of these languages are not written. There is no text available for them. The majority of these languages, for 99% of the languages, we have not enough data, texts, or transcriptions and annotations to train anything like a part-of-speech tagger or a dependency parser or stuff like that. Resources are not there. Nobody does that. Some of my students who are sitting here know that, for example, for Bengali, 110 million speakers at least, for example, there's no resource that is like anything of that kind, like Spacey for Bengali. It doesn't exist. You will not get a dependency parser for that language. 110 million speakers. Economically highly relevant. Resources are not there. We don't even know whether our common algorithms that we write and test work actually with those languages. We have no idea. We don't even know a lot. Actually, their grammars are not even described. The formal properties of the languages are not described. Not to talk about the acoustic and perceptual properties, the speech properties. Linguists were accused of focusing on rare and artificial phenomena, rightly so. They would look at strangest constructions that you would never hear or observe anywhere in the world and write PhDs about that and so on. Constructions are totally irrelevant for anything in NLP. But on the other hand, stat NLP often focuses on shallow and trivial properties of language and still just gets about 80-90% accuracy. So there is sort of a tension between these two. If we look at Google Translate, it was more or less a joke up to recently, and it's now becoming better. This was not quality translation. This was not good NLP, what they were offering us. Google Dependency Parser. Well, they were very proud to report that they do now 94% accuracy on the Google Web Corpus. Well, toss in a sentence of 14, 15 words, and they get 0 accuracy. It gets worse and worse. These models are not top-notch, and this is just dealing with dependency parsers. It's not dealing with high-level, deep semantic properties and feature extraction. And current AI applications know better. See, I'm playing with all of them. So I'm using Alexa. And I told this to friends here already. I cook with Alexa and I say, Alexa, set the timer to 5 minutes. And she politely confirms and sets the timer. After 5 minutes, the timer beeps. Beep, beep, you know. And I say, Alexa, thank you. And Alexa says, you're welcome, and continues beeping. She has no clue about natural language pragmatics or speech acts whatsoever. And there are actually no people around there who know that, who could implement that to improve the AI. And so there are quotes that I took from Remy van Tripe and Katrine Boyles. Stat NLP is crying out for better language models. Some of you might know Charniak. In practice, especially if we count industrial labs, a strong trend is towards higher-level syntactic frameworks and hand-built grammars. Carroll et al. Stat NLP is a pendulum swung too far by Church himself. We need to put linguistics back in computational linguistics, Martin Kay. So these are all the big shots in NLP and natural and computational linguistics. Fernando Pereira, you might know, the director of Google Research. By ignoring finer details, our language processing systems have been stuck in an idiot savant stage where they can find everything but cannot understand anything. The main language processing challenge of the coming decades is to create robust, accurate, efficient methods that learn to understand the main entities and concepts discussed in any text and the main claims made. And so on. This is just sort of a summary of quotes from big shots in the scene who are telling you what's going on. We had a bipolar partitioning in linguistics and NLP over the decades, yeah?
Curious, maybe you don't want to say who said the quote about firing linguists, but I think it's one of those people you listed.
Yes, 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 yes. This was in the 80s and 90s, basically, the attitude, you know, by one of these guys who I listed there. There was what we were observing is a bipolar partitioning of linguistics and NLP. So basically, one was drifting into the area of knowledge of language only and focusing on that. Qualitative, in-depth universals, theoretical properties of language, complexity, computational properties, and so on, that are very theoretic, irrelevant for applications and engineering of any kind of NLP. On the other hand, the current statistical approaches only focus on language use exclusively. Quantitative and shallow properties are relevant. We are using corpora to extract information, annotations from experts, annotations from theoretically trained linguists. We are extracting with very simple statistical algorithms to apply them then, right? And we are calling that AI. This is just to give you the impression of, you know, and this is focusing on black box modeling approaches, which means that actually usually any of these models that I extract, the quantitative shallow properties from corpora, is a black box for my human understanding, for my rational understanding of how it works and what actually got extracted. Just think about deep learning networks and the models you extract from there. We don't even understand why they do certain things they do. Or maybe it's just me. The arguments at each level here, all sides were arguing we need to do that for robustness, for coverage, for dynamics. Languages are changing permanently. We have to cope with that. We can only cope with that if we have a rule-based system. No, we can only cope with that if we have a quantitative system, right? These were sort of the arguments on both sides. And they were declaring each other dead. Right, so these guys would say this will last another year or 10, you know, but then it will disappear. And they said these guys failed, you know, in the 80s, and this won't work anymore. Well, what we are working on, our goals is hybrid architectures. We are focusing on engineering of real technology parsers that we understand, that we can control, manipulate, tune, tweak, and so on. And we use machine learning and AI in a very different way, I think, that is different from the common approaches. And the common approaches would be take data, train on that data, and apply your models and your algorithms to new data. That's the common approach. We want to change this in our architecture. So we are working with linguistic models and knowledge of language, developing grammars using linguistic universals to process syntactic, semantic, and pragmatic properties of language, which goes beyond anything you can get nowadays in a dependency parse or similar things, or an n-gram model for that matter. Grammar engineering we also use in a way to induce rules, to induce system properties that we can actually parse and understand, and to build something on which we can semantically reason using common reasoning algorithms and strategies, which is what I call white box modeling. We can reason and induce lexical properties, grammatical rules, and knowledge in knowledge representations using such strategies. And the machine learning algorithms we use to create robustness over noisy data. And this could mean that we can learn unknown words, we can guess properties of unknown words, we can cope with ungrammaticality, dynamic semantic properties, balancing frames of verbs changing, the meaning of a certain noun changing, and so on. And then the next goal is to embed this all in some sort of high-performance computing architecture so that we can really sort of apply that in a real scenario at industry level. And so the existing platforms, you might not know about those, and for a good reason, because they were always locked up. So one of these platforms is the Xerox Linguistic Environment, XLE, and the Xerox Finite State Toolkit. Well, the Finite State Toolkit, the XFST, was accessible, actually. You could download and use it, but they had such a licensing condition that even the rules that you write with that, the grammars, the morphologies that you generate, belong to Xerox. And otherwise, you would have to pay a licensing fee and buy those from them. The XLE, the Xerox environment, used the LFG framework, the one that I introduced in the beginning, for syntactic, semantic, prosody, and information theoretic processing. Information theory here is not Shannon. This is actually a linguistic type of information theory that goes into pragmatics and semantics and so on. That here is used to write rules to process lexical items, to write word formation rules, to develop a finite state transducer framework that copes with linguistic rules to word formation, suffixation, infixation. A lot of work has been done on Semitic morphology with interdigitation, Hebrew and Arabic, for example, but also Turkish and other languages. There's another framework, the XLFG by Lionel Clément. That's here licensed. You have to make an agreement with Xerox, by the way, to get access to this technology. Indiana cannot make such an agreement. I used the Xerox technology over the last decades to teach and research with it. Indiana does not allow that because they are in California, and Indiana does not allow laws, agreements that require that laws of another state are that your agreement is subject to laws of another state outside of Indiana and so on if you're funded by federal or taxpayers' money. And so excluded. We had long discussions here 3 years ago with Xerox and IU lawyers, didn't work. XLFG is a system online. You can use it from their website. By the way, if you get these slides, all these terms here are clickable. They are hyperlinked. So you could go to all these technologies. Well, this is closed source. We don't even know how that works. We can apply it online. Again, the story is if I develop grammars and models, they belong to this guy. He owns them. There's a framework, the Fluid Construction Grammar Framework, Babel 2. This is used currently in ongoing research projects by DARPA, Department of Defense. They are using it in development of interaction systems, natural language interaction systems with robotics, because these models allow you to specify action items and real sort of actions that the robot is performing with a given speech act and so on. So what I was telling you about Alexa, not knowing that if I say Alexa thank you implies that you should stop beeping, these models allow you to formulate such actions actually and implicatures from speech acts. Another one that is high level and deep, this is the Delphin project, LKB, HPSG based framework, another grammar formalism. That's developed by colleagues at Stanford and the University of Washington. That has a totally in-depth coverage, is just an extremely complicated formalism. Well, we started our project by discussing with Xerox the licensing conditions, and when they said they will not license, we are legally not in the position to get a license from them. We said, well, then we have to reverse engineer your system. And they said, yeah, good luck with that. And this took us now about 2 years. So we are at the stage where we are we can parse their formalisms, and we have a much better system in the end. I'll explain why. So Xerox closed source, many compatible morphologies. A lot of people, a lot of industry has worked with that. There is technology out there that is going beyond core NLP, SPACY, and NLTK that is used in industry over the last 20 years that is based on the Xerox technologies. And they are in-depth, they are sold for a lot of money and so on. We used to work with them, we used to teach that actually. Unfortunately, as I said, we can't do that anymore. A colleague of ours from Holland already reverse engineered this XFST system for lexical processing, and you can download it now as FOMA, open source C implementation, very efficient. That's a component that we are using in our system. The XLE system, the grammar parser system, again, owned currently formally by Microsoft, supposed to be used in Bing, is strictly licensed, pseudo open source. Well, if you want to see the source, you have to sell your house and sign off everything you own and I don't know what in the non-disclosure agreement, you know. And it's missing actually a probabilistic modeling framework or infrastructure. But again, you have tons of grammars that are deep grammars for this formalism. English and Arabic and so on. And so yeah, this is what we reverse engineer as FLE. And change in a very different way. Now, LFG as a formalism never had any kind of stochastic or probabilistic modeling capabilities. Was not foreseen in the theory when it was developed. This was the pre-probabilistic phase or epoch. And so there are certain attempts, but nothing of that has been ever realized. There's no implementation at all. And there are no corpora actually. There's no data set that we could use to train from or to evaluate our parser on and so on. So this is something that we really have to develop now, going in this direction. So we combine basically the white box and black box modeling. That's what we want to do and reach this white box transparency. And of course, this is linked to cognitive and psycholinguistic modeling. I'll say a little bit about that if you want. I can explain this in the question period. And go into the details. So we started developing tokenizers for different languages. Now here, whoever knows Chinese, you know that you don't use white space for that, Burmese neither. So if you want to tokenize Chinese or Burmese, you have to come up with a smart technology or algorithm. One of our students here developed the Chinese segmenter. Lwin up there is working on the Burmese one. Morphological analyzers, I will give you an example of what they do in a second, are things where you toss in a word and it gives you back the lemma and the feature structure of a word, or you toss in the lemma and the feature structure and it gives you back the surface form. So it's bidirectional finite state transducer technology. That's what we're working on. And then grammars for tons of languages. We map everything on weighted finite state transducers in the back end as the parsing technology and have various parsing algorithms implemented right now. We are coding everything in C++ 11 or newer. It should work even with Microsoft Visual Studio. I tried for weeks to get it to parse, to compile. It didn't work, but it's just my mistake, I believe. It's all CMake based. We use the BNFC system to sort of define the grammars of the formalisms and compile them then into code. This gives us the flexibility that we can switch to any kind of language, C, Java, Haskell, or so. We document everything in detail, Doxygen-based. This is not common for academic projects, I tell you. And everything is on GitHub and Bitbucket, so you can share it and join us in the development project. We use usually the Sea Lion IDE, which is free for academic use for teachers and students. And you should compile on any system. The dependencies are the C++ standard libraries, Boost, and FOMA, the new finite state transducer compiler for morphologies. That's the only thing. The rest we coded ourselves. We can plug in other tokenizers for different languages and so on, but independent. So what is possible, we can build a pipeline, we can toss in a sentence, get it through the tokenizer, get every single word through the morphology so that we get the morphological analyses, the feature structures, parse that whole thing and get some sort of semantic representation. That's a nice standard pipeline that Spacey does and all the other tools. The real architecture that I'm after is something which is based on the parallel architecture of the language faculty model by Jakendorf and colleagues, where basically all the linguistic components are independent modules that are processing something that is on some Blackboard system or a message passing system, and they understand the message and they process it and generate a representation. And what we have is a general constraint satisfaction model over representations. This has a cognitive background and it has a linguistic theoretic background. That's not necessarily the most performant system, usually because of slow Blackboard and message parsing backends, but it has a different idea. We use basic tokenizers like just tokenize on white space, but we can use finite state transducers using the FOMA framework to use lexicons or dictionaries from languages and guess where words are in an input string, in particular for Chinese and Burmese. That's an easy approach, not very efficient in the sense of generating a lot of noise. We are working on those, as I mentioned, and a lot of tokenizers are basically covered by this open source freely available UCTO model and tool. The morphologies themselves, we have a lot of morphologies, a very big English morphology. We started developing a German morphology. I have developed a Croatian morphology some time ago that I'm porting currently onto this FOMA-based framework, that it's all compatible and standardized, and then we do that same thing for Chinese and Burmese. I said that some students are working on Swahili and so on, and broad coverage morphologies you will find for Arabic, Malagasy, Polish, Norwegian, and so on, English as well from others. The Arabic one was released as open source by Xerox, and it's extremely good. So this is one of the best morphologies you will find around on the open source. It's on SourceForge for download. That's an analyzer that we have that basically uses the finite state transducer that rewrites something like Tim into something like this, where you have category information, feature information, and then typing of named entities and so on. And it does, so this is the input list of tokens, and it does also multi-word recognition. And we have databases in there that classify named entities with respect to business types and so on. That this guy here is of named entity special type business, for example, and the whole thing, Tim Cook, is actually a person name. So you get sort of hierarchical structures from the morphological analyzer out. This we feed with tons of databases. It knows all the toponyms, place names, and so on the planet, as well as large scale of names and so on, general names, but also business relevant names and so on. The grammar, the parsers for the different grammar formalisms we developed using the labeled Bacchus Now form, which is just another, it uses just an extra label in front of a normal context-free rule in the Bacchus Now form, and generates you from this label a method of a class, which is in this case using visitor-based parsing as a strategy. We map all the grammars the grammar formalisms on weighted finite state transducer models. That's just everybody knows what finite state transducer is. That's a slide that is less relevant for us. But that is sort of the grammar formalism, for example, of a real rule that says that we have a sentence and here's an epsilon transition, here's a noun phrase, and here's a disjunction between verb phrase and auxiliary phrase, right, for English. And these are the corresponding feature structures. Here's an optional noun phrase, in fact, actually, as well. And that's corresponding to the previous rule set that I was showing you. We parse those into such weighted finite state transducers where we have the upper tape and the lower tape and the weights for every transition. Here all weights are naturally set to 1. There are no weights on the states or on the final state in particular. We could add that, and I'll show you on the next slide how this works. So we map a production grammar by, say, for example, mapping the right-hand side on the left, on the upper tape, and the left-hand side on the lower tape. So whenever we process a sequence of symbols like MPVP, we emit an S with a certain weight, right? We map a complete probabilistic context-free grammar this way by attaching to the final states additional weights. So we have transition weights and emission weights on the final states. This here corresponds to a rule that has a preposition, a noun phrase on the right-hand side, and a preposition phrase on the left-hand side, right? This is how you process that. The E's here are epsilon transitions, so you're not reading or writing anything off. You read those probabilistic grammars from tree banks, for example, like this. This is a snapshot of the Penn tree bank, so we could read out an S, we could read out an S left-hand side with this and this as its corresponding right-hand side symbols in sequence, count them, and have a probability associated with the rule. Now, in our system, we can use probabilistic context-free grammars of this type, read rules out from a tree bank, but those rules are not containing recursion, and recursion we consider some natural concept of language, right? So you could say a noun phrase of English consists of an article and 0 or unlimited number of adjectives followed by a head noun, right? And so that kind of recursive definition of a noun phrase is not possible in the PCFG rule that you extract from a corpus. It doesn't exist there, right? You could accidentally end up having recursion in PCFG rules, by the way. So every rule has its own probabilities. What we can do in our system is we match the transition probabilities with weights. So here, for example, let me give you an example with the adjective. There's none. I didn't put in any rule like that. Here's a noun phrase that can contain optionally a determiner, an article, followed by a head noun, and then followed by one or more preposition phrases. That's a recursive system. And in a probabilistic context-free grammar, this would have the same probability no matter what, how many times you apply this preposition transition here, because it's not coping with that as a concept. In our system, every time you go this path, you multiply with a new weight, and the weights go lower, and it will be less and less probable. So that's just what we are saying here. If we have a rule that looks like this, MP is an article, unlimited number of adjectives followed by a noun, that probability is higher than that one here in such a transitional system. We have implemented an early unification parser that copes with the LFG feature structures. That's based on unification. How you combine those, we map those on directed acyclic graphs. However, the directed acyclic graphs for unification, let's now think of this as the attribute value matrix, the root, and it has an agar value that contains two sub-feature sets, number and gender, with these values, right? Now what we do is actually we weight the paths. So something like a sequence subject agar num equals plural, so this would be this path here, is a certain probability for subjects and another probability for objects over general feature structures. This allows us now to quantify, to build a probabilistic model over feature distributions in general. And first time now, basically, we can naturally build a probabilistic model of an LFG parse, which is basically the likelihood for any given input sentence that you get a tree structure, right? A C structure, constituent structure, and a feature structure. We represent both as probabilistic models. The product or whatever model we then build on top of that, we could use to come up with a real probabilistic LFG. We could train and evaluate actually such feature paths. I don't think that any other algorithm currently in the syntactic parsing scene does anything like that. The backend syntax properties are, we currently parse CFG backbones, but we can extend those. We can easily actually add mildly context-sensitive backbones or even real context-sensitive backbones if we think that this is necessary, say, for example, for semantic processing and so on. The weighted finite state transducer model in the backend allows us to do that. And then, of course, yeah, we can calculate feature probabilities. What we can't do now, this is a real example what the parser gives out. Such a parsers, you can test this one here is XLE Web on the website. If you search for that, this input was every man loves one woman. And you get such a C structure, that's the sentence structure, and this is the F structure for that. And you see that you have a lot of details in here about the individuals and so on. But, and it gives you a shallow semantic representation, but it does not tell you these two things here, and this is that this sentence is ambiguous. So it doesn't, this analysis doesn't explain that one interpretation is that the universal quantifier has scope over the existential quantifier, which is that for every man there is exactly one woman, such that X loves that woman. That is, everybody loves Marilyn Monroe or something like that, right? The other interpretation here is there exists a woman, the existential quantifier has scope over the universal one. There exists a woman such that every man loves that woman, which is basically pairwise. So this would be like for every man there's a woman, or there could be any kind of mixtures or so. These semantic interpretations don't exist in our parsing output. So what we need to do is process that and generate such expressions to map them on such real semantic content interpretation, right? That can be computed and processed further on. Currently what we have is a Bitbucket or a GitHub repo, many ready components, tokenizers for Mandarin, which works very well, Burmese start of that, and the others are just generic and should work without any tweaking and so on. We have morphologies for English, a base morphology for German. We started working on that to cope with dialects and variants like Indiana German, Texas German, and so on. We have a morphology for Croatian and broad coverage grammars and morphologies in the XLE and XFST format all around that we can use, as I mentioned, Polish and so on. I just measured this morning altogether in the repo we'll have something like 560,000 lines of code, usually C++, some Python and shell scripts and so on. The entire code, when you compile, for example, the morphological analyzer that runs the single tokens through a finite state transducer, what we get on an i7 CPU on a single thread is about 300,000 tokens per second for the lexical analysis. That gives us actually ambiguities as well. I can demo that if you don't believe me. If we parse with C structures and so on, we get about 3,000 sentences per second. And this is just a single thread on one CPU, which we have to now, of course, port. And so the goal, what we started working on or thinking about, is trying to use Cocos as a C++ programming model for performance portable applications. That's an abstraction layer that sort of allows you to program such that when you compile during runtime, the compiler will figure out what your configuration is, whether you use OpenMP or whether you use CUDA and so on, and it will generate you the best performing binary application on your platform, whatever you have there. And that's an ideal model, actually. recommended also by some colleagues here from high performance computing. That's how I got to that. We are mapping the FST-based morphologies and feature unification algorithms with trees, with the DAGs and so on matrix operations, which would allow us also to do high performance operations on that, say on, in particular, unification is a time consuming operation. We could sort of push this out to a GPU, for example. We are guessing syntactic categories using machine learning algorithms. We could use neural networks for that as well. Currently, we're just using some hidden Markov models and so on. That's impossible currently. We can't learn from corpora. We don't have those. We'll have to create such corpora that contain the information that we actually use in these parsers and in our grammars. That's it. And if you want to join that project, there's a lot of room for all kinds of stuff. Students join that, write papers, have presentations on conferences. It worked out for some didn't. So, thank you. Sorry.
So when you're constructing the LFG, right, how is it different from, say, a dependency parse? Because
well, you know, a dependency parser, a dependency grammar as such, basically describes functional relations. So you have a root that could be a verb that is, say, what did we have, love, and you have a subject of this, John, and an object, Sue. Now, all the dependency parsers that I know are actually just trained on manually annotated texts, where linguists just go walk through the sentences and annotate such functional relations. These relations do not describe, although it looks like they do here in this case, word order constraints. Right? So it doesn't matter where John is and where Sue is. They could be in the reverse order, Sue, love, John, or whatever. Right? So these formalisms are not designed to describe word order constraints in the first version. There are extended versions where people claim that you have to maintain the linear order that you observe in the input sentences and so on. But that's not what the theory is designed to do. It's designed actually to cope with free word order languages like Czech and some other Slavic languages, where the assumption was that only these things are relevant. You know, if you take Swahili and some other languages, we had this discussion just today in some other class. This is what you observe. You can permutate all words in the sentence the way you want. And, you know, the only thing you want is reconstruct these relations. In the LFG parser, we are doing, of course, totally different things. So we are constructing trees. And in these trees, what we code is semantic relations. So she killed the man with the tie. That would be a sentence that is ambiguous, right? So one interpretation is the killing happened using the tie as an instrument, or she killed the man and the man had a tie, and the other man who was not killed had none, right? Now this relation we describe in the sentence by saying in the first interpretation what we have is a verb, kill, and a noun phrase, the man, and a preposition phrase that is the instrument with a noun phrase, tie, right? And what we describe in this structural representation here is that this is modifying the verb, the predicate, the action of killing, right? The other interpretation is basically that we have a noun phrase that has a preposition phrase modifier with the tie. And this means that the man had a tie, right? These are structural representations. We describe the ambiguity of this sentence as a structural ambiguity, right? There's no way you can do that in a dependency parse. This doesn't exist. You would have to introduce multiple layers and have some sort of multi-stratal dependency parse model over the input sentence. That's one positive effect of using a combined version of, say, LFG that combines the structural representations with a feature representation that is a superset of these relations that you see here. Right? So we are combining that actually in one parser and one formalism. And those we engineer, we write those rules, we don't learn them, but we can learn them. So I didn't say that. One thing that I'm interested in is read that from a corpus, train this model, right? So read the rules out. But another thing is I can engineer the rules and I can run them through data and train weights by running the parse. You see what I mean? So I could learn when I'm processing normal text and I'm generating parse trees, I could train the parser to tune itself by just, counting itself how many times it applied a certain rule, how many times it got to a certain feature description and so on, internally, right? This is a very new approach that has not been, there's this sort of internal tuning or training without annotated corpus.
Is the LFG generic enough to capture any language?
Well, yeah, should be. I mean, of course, you idealize, there are languages where it's hard to say this word is a noun, right? Where a word is ambiguous between a verb or a noun. And say in Japanese, if anybody knows Japanese or Korean, you have suffixes like ba and ga that are marking up noun phrases, right? And people call this nominative marker. Well, it's not really the case, actually. It's much more than just a nominative marker. But if you have the English glasses on, right, and you're looking from a West European perspective on this language, you might call that nominative. So this is an idealization that we apply, right? But if you're looking in depth at languages, you will see that there is a lot more variation and a lot more deviation from any kind of English standard or German standard or so than you think. And so whenever we do model language in grammars or in anything, and whenever we annotate even dependency trees like that, we actually idealize. And we apply a certain model or theory on that. And this might not be sort of the ideal best thing for the language to do, but you said something, go ahead.
Well, I had his question, but I do have another question, which is, what's the motivation for using a finite state transducer over doing a CFG parsing for the PCFG?
Yeah. So the model for the grammar and for the morphology. For the morphology, I said already, you toss in a word, a surface form, and it gives you back the lemma and the features, right? Because it has basically the upper tape is the surface form, the lower tape is the annotation, the analysis. You can reverse it, so you can generate with it, right? If you have a grammar mapped on a finite state transducer as well, you can do that same thing again. You can actually, just by reverting the tapes, make it a top-down parser or a bottom-up parser, And what we wanted to say is once we have a feature structure, one of these LF structures where we translate the predicates, we can toss it back into the grammar. That's what we want to achieve. So we want to have a finite state transducer that generates us back surface forms of sentences. As in pargram or so.
Mm-hmm.
Any questions? We're out of time anyway, so thanks so much for the talk.
Thank you, guys.